see, we're going to talk now about the well completion workflow with AlanaPy. In previous sessions, we talked about that Alana has the ability to store multiple tables that in order to keep building complex workflows to kind of link data, oil field data, energy related data to it, we can really kind of focus the storage to our need, to the project that we are currently working on and we are developing. So I'm just going to stop this kernel. We're going to go back into the well completion notebook that I've created for this session. Okay, I'm going to clear the kernel just to kind of keep things simple. I'm going to discard. There you go. I'm going to rerun the importings of the fundamental libraries, the AlanaPy. I'm going to provide once again with the Alana token, and we can keep moving forward with this subject. So as I was saying, we can kind of focus the storage to the project that we were working on. Voice out there. So in this case, we talked about that we have in Alana, currently we have the well completion table. The well completion has, as the name says, the completion data for the fields, the projects that we want. In this case, I uploaded the well completion data of the Argentinian data that we kind of developed a couple of weeks ago. So we're going to work and we're going to develop that workflow right now. And to see what Alana has to offer, what Alana can do in this case with this well completion table. Okay, so as you can see, let us think back. Let us remember that we're going to request information to the data set, to the database. We have instantiate my API, and if we go to my API, we go into the for example, here we have get well master and so on. Here we have a function called get well completion. Okay, we select it and we check its docstring. It says that the function, it's a function that fetch the well completion data of a given well name. The arguments are the well name, and in response we're going to get a list of dicts. Okay, let us in this case we're going to request a well name. So first we're going to create a line of code that will fetch the well names that we want. In this case, let us remember that the master has a well master dict, and I'm going to request its keys. This well master dict, let us visualize it. We have the key and its ID. In this case, I just want the keys. So I'm going to get in response this, but I want to transform it into a list format. Simple as that. And I'm going to just print, for example, just to visualize the first, the last three elements. There you go. So I know that this function works with well names. So I'm just going to, for example, I'm going to ask the well completion for, I don't know, the 100th, the 200th well in this list. Let us see if we have the completion data of this well. And as you can see here, we have in response the block affirmation key. We have a top and a base. We have fluid type. We have a fluid, label as well. We have the state, we have intervals, we have the situation, we have a prod zone and its current WellFK, which as you might remember, this WellFK, it's associated with the well name. Okay, so as you can see, we are requesting the server, we're requesting Alana for the well completion data for this well. So what I'm going to do is, what happens if instead of giving this this name, I don't provide this function with anything. So I'm just going to test it for you guys to see it. Well, must get well completion. I'm going to leave it empty. The API is working, it's requesting the server for something. In this case, if we don't provide anything to the function, we are going to request all data, all well completion data that is stored in the database. We have a lot of wells here. We have a lot of data that we can analyze with this engine, with the Python engine. Okay, so I'm going to transform this. We know that pandas offered the function data frame, and if we provide this function with a list of bits, we are going to be able to see the function, this structure in a data frame form. I'm going to store this on a variable called df well completion. Going to be equal like to this, and just to visualize it as well, df well completion dot head, and just show me the 5 rows. And let us analyze it in a much more neat way. As you can see, we have several columns: block, formation, top, base, fluid type, fluid, and the columns that we saw. This fluid goes for the first, the initial rate of production. Looks like the state. What if we want to analyze the contents of this table? So I'm going to first create a very simple. I'm going to add a line. As you can see, we're talking here about WellFKs. Wow, we don't want to do that. We want to work with well names. So let us remember that in the previous sessions, I told you that we have several stored data on your local computer that you can access through the master. And here we have the IDs, well names, IDs, well names. What is this? Well, it's nothing more than the ID, the WellFK, and the well name. So if I just add this dictionary to replace, and I'm going to replace to this replace function, I added to df well completion to a column. I'm going to replace all those. I'm going to replace all these WellFKs or these numbers to its corresponding values, which are the well names. And I'm going to store them in a df well completion in a new column called well something got erased here. Well completion. There you go. I'm going to run it. Well completion is not fine. Yes, I forgot to run the df well completion. Let us print once again this data frame, and we have the corresponding well name. Excellent, excellent. Looks quite promising. This. I'm going to create a very simple loop. I'm just going to explain to you guys the process, or I have it just like here. I'm going to explain how I developed this couple of loop. First, I created an empty list called empty calls, the empty columns of the recursive or the loop when I'm looping in columns. For column in this list, the df well completion columns, there you go, like this. I'm looping in these columns. And I'm creating a new list that has all the unique values that are in that column, okay? If the length of that list is much more than 5, just for visualizing purposes, I'm just going to print the first 2, and I'm going to print a string that says total unique values. And I'm going to print the length of that list. If not, if it's less than 5, it's going to print the same label, but instead of printing just 2 elements, I'm going to print all the list. Then again, for visualizing purposes. And if this list in this column or in this iteration, the first element is equal to a non-value, I'm going to append that into the created list empty calls. Why? Because I want to, for example, here we have a plot zone that looks like we have empty, we don't have any value. We have here the state that looks like we don't have any value as well. The top and base looks like we don't have a value as well. So I want to store those columns that has nothing to later on kind of remove it from the data from this data frame. Okay, I'm going to run it, and as you can see, the ID column has a lot of values. Total unique values 923. In the block column, we have only one, the Neuquina block of the Argentinian data. Formation, we have several. We have 5 values. All of those are referring to the formations of the data. Top and base, we don't have anything. We only have one value, which is none. The fluid type, we have either conventional or unconventional. So we have only 2 values. Fluid, we have several, 126 different values. State, we don't have none. We have none values. Intervals, we have several, 585. Situation, we have either exploration, advanced, extension, development, or control. We have 5. Plot zone, we have nothing. And the well of case, the corresponding well FK that goes with the well names. Excellent, excellent, excellent. I'm going to drop. I don't want to see that well FK anymore. So I'm going to delete the well FK with the drop command and indicated that it's the column axis and just in place it. Okay. I know that I created a list of empty calls that are top, base, state, and plot zone. Why? Because I don't want to visualize the statistics of these columns. Okay. I'm going to use now, as we used in previous sessions, in the past week session, I'm going to use Plotly. Why? Because Plotly offered a very interesting way of visualizing statistics. I'm going to create a for loop for call in list of I'm going to paste this, and I'm going to tell you guys what this is. First, I'm going to ask with the columns property all the columns that are in the df well completion, and then I'm going to difference it. I'm going to kind of set apart the list empty columns list from this first column. Just for you guys to see it, I'm going to print. And if everything works fine, we won't be able to see either top, base, state, or plot zone. And as you can see, we have just done that with that very simple statement. Okay, now just to kind of check everything, I'm going to add a condition here that if the column is a data type object, it's not a numeric. I'm going to print it. And we're going to see it in kind of the categorical values of each column. So that's why I did this very simple condition. If it's an object, you go and get its counts with the value counts property of this data frame. And I'm going to do using the plotly a pie plot that has those values and those names with its title, and I'm going to show it. I'm going to run it for you guys to see it. Oops, yes. I placed two times, I paste 2 times this. There we go. It's running, and you can see that we have block, we have the 100% of all the values are for Neuquina. We have for fluid, for some reason, well, actually not for some reason, the fluid, we didn't do the classic dfwellcompletion.info to see the data type of each column. We have several objects. And for example, here the fluid looks like it's an object as well. It's not recognizing that it should be a float type data type. But I mean, we can change that fairly simple. We can see that, for example, fluid type, we have unconventional and unconventional. The conventional, it's 20.2%, which goes for 186 wells in this database. We have 737 for unconventional wells. We have several formations: Vaca Muerta, QTUC, SBLA, CENT. We have LOTE as well. For Vaca Muerta, we have 703 wells. We have situation, development, advanced, exploration, extension, and control. The development goes for 857 wells. Let's remember that we can kind of change some visualizing parameters with Plotly as well. And we have several well names. Unfortunately, this is an object, so it's plotting as well the well names, which if we kind of hover just for the sake of visualizing, we are able to see that for this well, we have a value of 2. What does that mean? We are going to do in a couple of minutes, we're going to check that the Alana has the ability to store if the well completion has changed in time, or maybe the completion process required several intervals or several formations. We can store them, or Alana can store them as well for for visualizing in a kind of sort of a visualizing tool, and to create maybe checking the well status, maybe checking the well, all the data, all the tables that we've checked before, if the production is commingled, or maybe they closed one interval and they went into another formation, and so on and so forth. So we are going to do that. We're going to cover that in a couple of minutes. Just to kind of continuing with the statistics, we can as well in previous sessions we use the cat plot. If we use the cat plot that we developed, list of calls, yes, of course. If we use the line of code that we code in previous sessions, we're going to see that. Let me copy this. I'm going to paste it here in list calls, run it, and we have the chart, kind of the histogram of this of this of this database. Fluid type, conventional nearly 200, unconventional plus 700. Almost kind of the same information in a different visualization form. Okay. Now we were talking that we have some wells that has several completion rows or several completion data stored, and as we can see it like here in this, we have the well name in the x-axis, and in count we have, for example, this well has a 2 count. This well has, we have several values that has more than 1 and less than 3 counts. How are we going to visualize that? Well, let's remember that pandas has a function that is called the group by, that if we run it, we're going to get like this group by structure for memory, which is an object. But I can tell that I want to count and I want to visualize the interval column. If we run it, we're going to see this. This means that for this well name, we have 2 counts in this column, in the interval column. Okay, I want to have like a much more much more easy way to visualize this series, which is this what I'm saying right now. So I'm going to add the PDF, the PD data frame. I'm going to construct a data frame using this, and I'm going to call it, I don't know, this is the data frame of multiple completions. Well, no, this is the data frame of completion. Let us call it df comp group completions. Yes, like that. Group comp. That stands for completion. I'm going to visualize it as well. And I'm going to visualize the head with 5 elements. Could leave it that empty, and there you go. We have, for example, this well has two occurrences on the interval column, such as this and such as this, and so on. Okay, excellent. That looks fine. That looks promising, but I want to filter them. How am I going to filter them? Well, we've done this several times before. I'm going to use this very simple state of filter the column and leaving, in this case, the df grouped completion. And we have a list of wells that has the condition of longer or bigger than 1 completion or occurrence in the interval column. I'm going to store this on a list, which I'm going to call list multi-comp. List multi-comp. It's going to be equals to this, and I'm just going to show from this list, I don't know, the first 10 elements. There you go. These wells have more than 1 interval in the database. I want to see why, so I'm going to ask for the DF well completion, the kind of the master, if you can call it like that. I'm going to filter a well that is inside this list to see how it looks. And for example, I'm going to access the column to add the condition that if this well name the value in the well-named column equals to, I don't know, let us call the indexed value of the 10th indexed value of that list. Let's run it and see what we got. And for example, here we have this well that has, in both cases, development situation. Intervals, for some reason, we have the same interval, but we have two formations here, QTUC and SBLA. This means, and both of them are in a conventional type. And as you can see here, we have the fluid in this formation, this QTUC formation, it's not producing anything. And this SBLA fluid column is indicated that we are producing, or they started producing from this formation, but both completions are available, or both completions are on the database. If we go and ask for, I don't know, the fifth, we have as well, in this case, the QTUC was a conventional fluid type completion, and these wells were exploration. And for the Neuquina, for the Vaca Muerta, the BMUT formation, which was unconventional fluid type, they kind of completed, and they didn't produce, they didn't get any production, or they didn't start producing from this completion. Then again, the situation kind of gives that away, because it's an exploration well. As you can see, we have covered several things. We can keep going further and further and keep analyzing multiple formations for the same well. We can keep adding, for example, as we're talking about this project-driven table formation, we can keep adding columns. Maybe we want to see if it's a single completion or a multi-stage completion. We have several completions. Maybe the equipment for those completions. I don't know. I mean, the things that we can keep doing are kind of endless. Okay, so I think that for this, that would kind of end this this session.